The last of our problems will be practice with distributive practice and of putting things together that we have previously learned, always known as distributive practice. So our fourth objective on our practice test A under solutions and colligative properties. The first example is titled the ideal gas equation, PV equals nRT, PUV equals NERT. And the reason I chose one of these is that it has already appeared in our colligative properties section under osmotic pressure. So a nice way to just kind of blend the two. It says solid calcium hydride, so CaH2, reacts with water to form hydrogen gas, and that's molecular, so there's our hydrogen gas, and aqueous calcium hydroxide, CaOH taken twice, calcium hydroxide. Polyatomic ion, OH, carries a -1. Let me take a moment and consider balancing. 1 Ca, 1 Ca, there's 4 H's, 1, 2, 3, 4, 2 O's, 1 O. Let's start by doubling our water to get the oxygens working, and that's 4, 5, 6 hydrogens, and then 2 and 2 is 4. How does that look? Check with me. 1 calcium, left and right. 2 oxygens, left and right. The hydrogens, there's 2 plus 4 is a total of 6. 4 plus 2 is a total of 6. So there we go. 1, 2, 2, 1, the way that I have it written here. It says this reaction is sometimes used to inflate life rafts, weather balloons, and the like, where a simple compact means of generating hydrogen gas is desired. So here's the desired product. Write the equation using adjectives. Well, it says solid calcium hydride reacts with water in the liquid form to produce gaseous hydrogen, either that little g or an up arrow, and then aqueous calcium hydroxide, so AQ for that solution. How many grams of calcium hydride are needed to generate 53.3 liters of hydrogen gas if the pressure of hydrogen is given at 814 torr and 21 degrees Celsius. So we have a volume, we have a pressure, we have a temperature. What we don't have for PUV-NERT is N, the number of moles. What we can do is a little PUV-NERT problem first, followed by a stoichiometry twist. So PV equals nRT, where we can pull out the number of moles of hydrogen that correspond to this set of data, and use that number of moles to go back into the calcium hydride moles and turn it to grams. So PUV-NERT first, followed by stoichiometry. Let's plug in what we know for PUV-NERT. Pressure was given as 814 torr. Volume already in a liter, quite large, 53.3 liter units. N is the target variable, and to remind ourselves that's N of hydrogen that we're generating. Gases have volume, pressure, and temperature. R to match the gas constant 62.4, and the Kelvin temperature 294 Kelvin units. Let's find N, where N represents the number of moles of hydrogen. So let me grab my calculator and hit with me, please. 814 times 53.3 divided by 62.4 divided by 294 Kelvin units. And the number of moles here comes out to be 2.365 moles of hydrogen. So let's use that now in a stoichiometric relationship with our given 2.365 moles of H2. And in the heart of our stoichiometry problem, we want over given. We see that every 1 mole of calcium hydride produces 2 moles of hydrogen gas. And to convert that out to a gram unit, we'll need the molar mass of calcium hydride, which is 40 from the calcium, 2 more for hydrogen, so 42 grams per mole. 2.365 divided by 2 times 42 gives us the number of grams totaling here as 49.66 grams of calcium hydride. So this problem gave us data for the hydrogen gas. We did a Puvnert problem first, targeting N, the number of moles, and that became the starting point here in our stoichiometry journey, turning moles of hydrogen into grams of reactant calcium hydride. The second of our distributive practice problems is a Hess's law, summation, little thermochemistry review. Given the following reactions, we have N2 gas plus iodine gas forming 2 units of NO. And delta H is given to us as positive 180.7 kJs of energy. A second elementary reaction gives us 2 units of NO, an iodine, and it goes on to 2 units of NO2. And its delta H, heat of reaction, or enthalpy, is 113.1 kilojoules exothermic value. Our target equation, the one that we'd like to solve for, says, let's figure out the heat of solution for, let me rewrite that, 4 units of NO producing 2 NO2s and N2. So what is the delta H of this reaction? What can I do to these 2 elementary reactions so when I'm done adding them together, we've indeed created the target, 4 NOs going on to produce 2 NO2s and an N2. So for no other reason than it's written first, I start looking at that reactant, NO. Where do we find NO in our equations? Well, I happen to see it in 2 different spots. Notice here, I have it written here and here. So it might not be the most useful thing, although if I flip the first, I get the quantity. So one thing I'm suspecting, just kind of talking through this, and I'm suspecting we're going to turn the first one around. Let's see what else. I noticed that iodines disappear because in my target I don't see iodine anymore, which also kind of supports the idea that we have to flip the first, because then I can get the iodines to actually cancel out. On the product side, I see NO2s, and I like that fact that I have the correct number and it's on the correct side in my elementary reaction number 2. And if I flip the first reaction around, I've got the nitrogen on the correct side. So could it really be that easy that we just flip the first one? Well, let's do that and see what happens. If I flip the first, it becomes 2 units of NO forming N2 and I2. If we leave the first one as is, 2 NOs plus I2 goes on to make 2 NO2s. Let's see what happens when we add those equations together. And as we suspected, the iodines indeed canceled. 2 plus 2 gives us 4 NOs. We're left with an N2 and 2 NO2s on the product side, which indeed is our exact target equation. So if we flipped the first, that first sign goes from endothermic to an exothermic value. And the second equation stayed as is, so it's also exothermic at negative 113.1 kilojoules. Adding those together, and we can hit that just to be safe, negative 180.7 plus a negative 113.1, and it is indeed negative 293.8 kilojoules of heat. There's one more problem in our distributive practice section. It is solution stoichiometry. Let's give it a read through. What is the molarity of a solution that contains sodium hydroxide if 28.2 mils of 0.355 molar sulfuric acid is required to neutralize. And again, as I read through this, I kind of ignore the numbers first, and I'm just going to pull out the chemistry. I heard sodium hydroxide is reacting with sulfuric acid. I have to get the chemistry down before I stand a chance of the stoichiometry. So I'm pulling out my two reactants. The base, sodium hydroxide, is going to be neutralized by a certain amount of acid called sulfuric acid. And we know that when an acid and base neutralize, the driving force, of course, is water and dissolved salt. So we have sodium sulfate as our salt and water written as HOH or H2O, your preference. To balance this equation, we're going to have twice the number of moles, giving us two values of water. Now that I have done that work, I can go back and kind of tabulate what we know. What is the molarity of sodium hydroxide if 28.2 mils of sulfuric acid that has a concentration of 0.355 molar units, and the volume of base that was neutralized, it reads as 25 mLs. What is the concentration of the base? It is not MV equal MV. We have a stoichiometric ratio of 2 to 1 units. So here's our given, and we work to what we want in our journey of stoichiometry. Start with the given. We know that 0.355 moles of acid are contained in every liter of solution, the very definition of molarity, moles per liter. If I multiply that by the volume in a liter unit, I get the liters to cancel and I have the mole. The heart of our problem says for every 2 moles of base, sodium hydroxide, it requires 1 mole of acid, H2SO4, a want over given ratio. Notice what's happened so far. Step 1, liters canceled. Step 2, moles of acid have canceled. Now, when we think about what's next, I have a volume of 25 mils. We want to know molarity. Molarity is defined as moles per liter. So let's just take that volume and set that under a 1. And now we get the very definition, moles per liter, which indeed is big M for sodium hydroxide. And let's hit that and see what we get. We have 0.355 times 0.028 times 2 divided by 0.025, and I get 0.7952, so let's say 0.795, I want to say just 0.80 molar units of sodium hydroxide. Solution stoichiometry review. And that does complete the practice test A from our solutions and colligative properties.